Okay, so just I am speaking today about atmospheric from satellites, but I will focus on ESA, and I will focus on satellites that are measuring atmospheric compounds. So that to give you just a little bit of history, then first atmospheric satellite that was launched by NASA was launched in 1960. This was a meteorological satellite and it lasted for a very short time. Now when we come to this atmospheric composition, the next more important instrument was TOMS, launched in 1978 by NASA, and from that we got the ozone measurements. MODIS and I both also NASA instruments, and again they measured aerosols and they measured clouds, and they were on top Terra and Aqua satellites. When we come to closer to Sentinel-5P, four heritage instruments, these are the instruments that can be continued by Sentinel-5 measurements. First was in 1995, our global ozone monitoring, which was launched by the European Space Agency, and it measured ozone, NO2, and clouds. And the resolution on ground was 320 times 40 kilometers. The next instrument that is important is Skiamachi on top of ENVISAT satellite, and this instrument measured already quite many different compounds. So we have ozone, NO2, CO, CO2, and so on. And the resolution was a bit better than GOMS. Both these instruments have been working by now, and the data series have been continued by OMI and GOM2. And both these instruments are measuring different atmospheric compounds, different trace gases, and aerosols, and also UV radiation. And even though OMI has been launched by NASA, it is connected also to different European agencies. For example, Finnish Meteorological Institute. And GOM2 is now ESA's mission. And now we get to Sentinel-5P, which is the main topic of this presentation. And Sentinel-5P is the first atmospheric composition mission in the Copernicus program. Main instrument on this satellite is TROP-OMI, or the Tropospheric Monitoring Instrument, and it was launched in 2017. And this is ESA's mission, and it is a hyperspectral push-broom imaging spectrometer with a SWAT width of about 2,600 kilometers, and it flies on near polar orbit. The spatial sampling is much better for this
Now it seems that Margit is back.
Oh, can you hear me?
Yes.
Okay. Was I lost for a while? Or? Okay, I will try to share my screen as this won't work. Okay, again. So, okay, so about the data products that are being measured on Sentinel-5P. The main products are ozone, nitrogen dioxide, SO2, CO, formaldehyde, methane, different cloud products, and aerosol information. We have aerosol index and also aerosol layer height. And here separately is brought surface UV. I will talk about the UV products a little bit later. These products are not in the same package as all the other measured products. So that's why it's in red, and I will talk about them later. All those products are available either near real time, so they're applied to the user 3 hours after sensing. And then there is also offline products that are available 2 weeks after sensing. But actually this time can be shorter. For some products it's 5 days, and there are even products that the time is just 24 hours. So it depends what product do you need. So the objective of this satellite mission is to measure air quality, to have these continuous measurements, to monitor constituents that are relevant to climate forcing, monitor ozone and UV radiation, and this data is input to different models in Copernicus atmospheric monitoring system, or so-called plumes, and also it is used for volcanic ash concentration monitoring. So about the current status of the data products. The last calibration validation meeting was in October. And before that, there were a few changes that have been taken place. Do you see the slides, or?
Yes, we can see the slides.
Okay, because I see a white screen, so tell me if it's no slides. The last major changes. The first one was the new spatial resolution. As I mentioned, the spatial resolution went from 7 kilometers to 5.5 kilometers, and this took place in August 2019. In July 2020, upgrade to universal processor was made, and thanks to this upgrade, Tropomi is now able to get new surface albedo. Before that, climatologies were used. Also, ozone retrieval from high latitudes improved. For formaldehyde, there was issues with sun glint, and this upgrade improved it significantly. Then cloud product improved over snow and ice, and in case of small cloud fraction and around cloud edges. And also SO2 product improved. And cloud mask was also replaced from VIRS VCM or VIRS Cloud Mask to VIRS Enterprise Cloud Mask, again to improve all the data products. And now shortly about the different products. So first of all, aerosol products. The aerosol index is working well when we talk about capturing the dynamics of absorbing aerosol plumes from dust, ashes and smoke. And in 2018, the data product was compliant with the requirement. But now the bias is actually larger than requirement because there is a wavelength-dependent degradation of irradiance. And this is something that is being dealt with. There have been corrections applied, and there is current work going on to fix this issue. Aerosol layer height is within requirements, but during the large fires in Australia, in New South Wales during 2019 and 2020, they discovered that there is a altitude limit of about 13 kilometers, as those bushfires produced smoke plumes that were above 20 kilometers. But there is no plan to fix this issue or to raise the limit. So it's just something that will stay like this for now. Then about formaldehyde, NO2, SO2, these biases are all mostly within requirements. There is dependence of the bias from the total amount of those gases being in the atmosphere. So there is mostly positive mean bias for clean areas and mostly negative mean bias for polluted or high emission areas. About the ozone products. Ozone, again, is in a good agreement with both ground and satellite measurements, and the bias is within the requirements. There are some differences in case of clouds with different satellites, as there are different cloud masks being used. And cloud models, sorry. And there is a systematic difference in case of high solar zenith angles. This is mostly concerning high latitudes and also uncertain ground albedo. Now we come to the UV products. These are developed by Finnish Meteorological Institute, as I said before. There are 36 different products being produced. So we have overpass and solar noon irradiance at 4 different wavelengths. Then we have overpass and solar noon dose rate for erythemal and vitamin D synthesis action spectra. We have daily accumulated irradiance at those 4 wavelengths. And we have daily dose for erythemal and vitamin D synthesis. Also, there is a UV index, but this is basically the same as erythemal dose rate. And all those products have been given also for clear sky conditions. And clear sky is considered as no clouds and no aerosols. And all the parameters are equipped with quality flags. Now, about the validation of these UV products. A large validation campaign was carried out and led by Kaisa Lakkala from Finnish Meteorological Institute. And this validation campaign was published just the end of last year, and I was a co-author in this paper. And it was published in Atmospheric Measurement Technique. So in the study, 25 different sites were included with a really wide range of areas. So we had stations from Antarctica, from Australia, from Indian Ocean, Europe, up to Arctic. So we covered a really wide range of different latitudes, also different albedo conditions, and to give a better overview how these products are working. Including so many stations was a bit problematic because they do not belong to some global network, but are mostly either independent stations or belonging to just partly to some smaller networks. So the station it was less than 1% for low and middle latitude sites and less than 2% for high latitude sites. There are also very different ground instruments being used. There are spectrometers, different kinds, and then there are different kinds of radiometers, and all these measurements are carried out on different frequency. So some measurements we have measurement in every 1 minute. In other stations there is in every 15 minutes. Also, the solar zenith angles above 80 degrees were excluded from this study. So for all measurements, relative difference was found, and the data sets were divided into subsets according to albedo. So we had either snow cover or no snow. And a separate subset was for cloud-free data. And each drop bomb pixel was treated as an individual measurement. And it had to, there were conditions set that this measurement had to, how long time could be passed between the ground measurement and when the overpass was gone, and how far the pixel can be from the station, and so on. So different constrictions. So here is an example from Belgium, station Appel, where we have a brewer spectrometer measuring, and here are erythemal dose rates. The red line is from drop bomb, and the blue one is ground. As you can see, the measurements follow each other quite well. And on the right here is the absolute difference between the ground and satellite measurements. And larger variation is during the summer when the absolute values are bigger. So that's why also the absolute difference is larger. But otherwise, it worked quite well. Here are the scatter plots for 3 different stations. On the left, there is Sodankylä, and in the middle, Helsinki. And on the right, Palmer station from Antarctica. The red dots are snow-free conditions, blue dots are for snow conditions, and black circles here are cloud-free conditions. And in Sodankylä and Helsinki, the correlation was quite high. So we have drop bomb measurements on y-axis and ground measurements on x-axis. But these measurements and the correlation was very different for different sites. And as you can see in Palmer, the situation is not as good as for Helsinki and Sodankylä. These are all spectrometer measurements. Here I just want to show you the results for radiometer measurements for different sites. Again, the red dots are for snow-free conditions, blue dots are for snow conditions, and black lines are for clear sky. And again, in some stations, the correlation was really strong, and then there were some stations that the correlation was really poor. This here is FINS, Data Third scatter plot. And FINS is in a mountainous region. And here this correlation is not good. So the results for this study, the spectral irradiances at the 4 measured wavelengths, the median difference was within plus minus 10% for most of the sites. For snow-free ground conditions. And all sites except one, this was Palmer, more than 50% of satellite data was within plus minus 20% of ground measurements. And there was a small negative bias overall for satellite measurements. So the satellite measurements were a bit lower than the ground measurements. And the main issues with the UV radiation measurements from satellites are using albedo climatology. So the albedo isn't taken from the simultaneous measurements, but just used pre-calculated climatology. Then issues arise when we have rough terrain, when there is mountainous regions. So in case of mountains, the 7x7 or 5x 3.5 kilometers pixel is large enough to have very different albedo conditions in the same pixel. Also, coastal high latitudes, when pixels include both ocean and land, then we have issues with satellite measurements. And when there are non-homogeneous clouds in the pixel, in case like we have change in surfaces, so above ground and above water, the different cloud conditions. This again brings issues to the calculation of UV products. Now about the Sentinel-5P data access and some examples how the data is being used. The main point to get the data is the Copernicus Open Access Hub. Right now there is a separate link for getting this Sentinel-5P data, but it's free for everyone. Everyone can sign in and get the data. UV data is available through Finnish Data Hub system. The link is brought here. Again, you have to register and get username, password, and then you can get the data. Here is one example I got from there. This is 15 August 2019. This reference here is just to the data. But this is got from the FinHub, and Panlopu program was used to get this image. And this is overpass erythemal dose rate. And yes, so that's what you can get from this Finnish Data Hub. So one of the big points of measuring with Sentinel-5P is so that it could be used in Copernicus atmospheric monitoring service. And finally, it will get to atmosphere data store. And so far, only ozone data has been assimilated into this COMS system for global real-time forecast. And one part of SO2 is also being used for volcanic activity monitoring. NO2, SO2, CO, and formaldehyde are being tested, so that in the near future they could be assimilated into the system, and methane is being considered, but not yet tested to be assimilated in this comms system. The main goal for Sentinel-5P is monitoring air pollution, and there is a Copernicus Sentinel-5P mapping portal where you can make maps of tropospheric NO2 concentrations averaged over 14 days. Here I have average concentration from 22 March to 4th of April this year. There is also an opportunity to do these maps for CO, so carbon monoxide. And most of you have probably seen this figure before. These are mapping of COVID effects on air pollution. And this is for NO2 over China. On the left, we have February 2019. In the middle, February 2020, when the country was in lockdown. And again, February 2021, when the country was opening up again. So there is this difference. There's actually was an article just recently about these COVID maps and the effect maps. And it said that users often use all the data they can get without considering these quality or uncertainty estimations for the data products. And sometimes this COVID effect comes out larger than it actually is, just because data with large uncertainty is being used. I don't think it's the case for this map, but just in generally, as it is being used quite a lot. Again, here is COVID effect on air pollution for SO2 over India. The black dots are for power plants, and on the left is April 2019, and on the right, April 2020, where again, the country was not so active. And you can see the difference between the 2 years for different pollution levels. One more example about the NO2. These emissions or these measurements have been used to estimate or to show the individual ship pollution from ships. So these red lines here, these are all individual ship plumes of NO2 over Mediterranean. And methane product has been used by companies to estimate leakages from natural gas pipelines. So we have on the left, there is Sentinel-5P data, and on the right is Sentinel-2 data. So we can see this plume is from leakage from a pipeline. And the resolution is just good enough, first time in satellite measurements, so that these kind of individual plumes can be detected. And one more example of ozone measurements. It's used to monitor ozone hole. This one is from 2020. This was one of the largest in recent years, opposed to, for example, 2019 was one of the smallest ozone hole. So there's a really large variability there. And this is, again, Sentinel-5P measurements. So what is coming for Sentinel-5P this month? improved level 1 and level 2 products should be released. And in the middle of this year, ozone profile product should be released. So these are the next steps for Sentinel-5P products. Now, about the planned atmospheric missions, or what's coming for the measurements of atmospheric composition and trace gases and aerosols. First, or the next one, is Sentinel-5, which should be launched in next year, in 2022. And the Sentinel-5 mission will be very similar to this Sentinel-5P mission. There will be the products that will be measured will be almost the same, and the resolution of these measurements will be also planned 7 times 7 kilometers. We'll see how it will be by the end. And this is again this near polar orbit satellite. And the objectives of Sentinel-5 are also the same as for Sentinel-5P. So the main focus is on air quality and all the data that could be used for air quality monitoring to issue alerts, and also this monitoring volcanic activity. After Sentinel-5 in 2023, Sentinel-4 will be launched, and this will be the first geostationary air quality mission over Europe. In the middle here, you can see the area that will be covered by the measurements of Sentinel-4. So most of the Europe will be covered, except the northern part. And this will have a spatial resolution of 8 times 8 kilometers. And again, the key products are brought here, so different trace gases and aerosol. And one more thing is that Sentinel-4 will give 1 hour temporal resolution measurements. So the objectives of this Sentinel-4 is daily production of near real-time analysis and forecasts for air quality over Europe. Again, it can issue alerts in case of bad or poor air quality. Again, monitoring volcanic activity and determination of sources and sinks of atmospheric pollutants. And this Sentinel-4 will be part of geostationary air quality constellation that will include 2 more satellites. Tempo over America, and this belongs to American agency, and GEMS that has already been launched and is measuring, this belongs to Korean agency. And the advantages of this geostationary air quality constellation is that it measures hourly data, which is much better than daily data that we can get from current missions. And it will give possibility to monitor short-lived tropospheric trace gases and aerosols. And these geostationary satellites will be supported by polar orbiting satellites, Sentinel-5P, Sentinel-5, OMPS, and EMI, and there is some other satellites that are being considered. So there is a really wide variety of data sources and different temporal resolution, and also different spatial resolution a little bit. And the timeline for this constellation is brought here. So we have GEMS already measuring, Sentinel-5 going up in 2023, TEMPO in 2022. And then the blue ones are these accompanying missions that are being used. And finally, I will talk about shortly about CO2, as none of these, or most of these instruments do not measure CO2, but as CO2 is very important trace gas for, especially in context of climate change. Right now, there are a few missions that do measure CO2. The most important ones are GOSAT, that belongs to Japan. And then there is OCO2, belonging to the American agency. And the last one that was launched was OCO3, that is mounted to International Space Station. And from the literature, OCO2 is right now the best instrument. There are additional instruments that do measure CO2, but the data is restricted, so we don't have free access to all the data. And NASA is planning a geostationary carbon observatory being launched in 2022 with resolution of 5 to 10 kilometers. The issue with instruments that are measuring so far is either they are not accurate enough, or the sampling is too sparse. In case of OCO2, that has really good accuracy, is that the sampling is really sparse. We have tried to look at data over Estonia over some objects, and because of CO2 measurements can be done only when there is free sky with no clouds, then you can really get only a few data points over a long period of time. So it's not really useful for this kind of continuous monitoring. And these problems should be solved by ESA's next mission on CO2 with much better sampling frequency and also better accuracy. The mission that ESA is planning and has agreed on is CO2M, or Copernicus carbon dioxide monitoring in cooperation with EUMETSAT, and this mission should be launched in 2025. The products that will be measured is CO2, methane, NO2, and solar-induced fluorescence. And these measurements will be done on resolution of 4 square kilometers or 2 by 2 kilometers, and aerosols will be measured with a spatial resolution of 16 kilometers. And also clouds will be measured, and the simultaneous measurements of aerosol and clouds will give better results for those trace gases. There is also capability to measure glyoxal and water vapor for this mission. And the data from this mission will be used to help track and implement targets set out in the Paris Agreement. There will be detection and monitoring of emitting hotspots, assessing emission changes against local reduction targets, and assessing the national emission and changes. And for CO2, it is important to remember that satellites measure only atmospheric concentrations, and they do not really measure emissions, but they can follow this change in concentration and therefore in emission. And the measurements can only be done during cloud-free time. So there are some limitations. And that is it from me. Thank you.